Hello everyone, welcome to chapter 8. So in this lecture, this chapter is electronic configuration and chemical periodicity. So in this lecture, we'll talk about the characteristics of many electron atoms, the quantum mechanical model and the periodic table, the trends in the atomic properties, the three main atomic properties and the chemical reactivity. So the one quantum number that we did not discuss in the last chapter was the spin quantum number. So the spin quantum number is the number that determines. So next let's discuss the spin quantum number. Here is the number that determines the characteristics of an electron passing through a magnetic field. Now an electron by itself, when you take the electrons in a hydrogen atom, every electron will either have a positive spin or a negative spin. So the positive spin basically says that it goes towards the south side of the plate, it bends towards the south of the plate, and negative spin says that it bends towards the positive part of the negative part of the north part of the plate. Now this idea of having an external non-uniform magnetic field interacting with the structure of the electron itself is something that boggled people for a long time. But understanding this gives you a simple understanding of how electrons themselves behave. So spin quantum number here is, there are only two numbers, either it can be plus half or minus half. It basically says that if you have an electron, the electron by itself does not stay stationary. It actually rotates. That rotation can be either anti-clockwise or the rotation can be clockwise. So this clockwise or anti-clockwise is what we write it as plus half and minus half. So if there is a single if there is a atom with two electrons, so that's the reason why whenever you see an electron, the electrons by themselves in orbitals stay as pairs. So the pairs here, meaning that one will become anti-clockwise, the other rotates clockwise. You will never find two electrons that are always going to be in the same spin quantum number. So we discussed four quantum numbers. Principal quantum number, which has positive integers. It has the orbital energy, it generally shows you the size of the orbit. Angular momentum quantum number, L, is the integers from 0 to n minus 1. It determines the orbital shape, whether it is 0, 1, 2 and 3, which is representation for S, P, D and F. Next we talked about magnetic quantum number, which determines the orbital orientation, so which is from minus L to 0 to plus L. And you have spin quantum number, which there is generally two numbers, plus half or minus half. It shows the direction of the electron spin. Now, what can we use these quantum numbers to determine, and what are the rules that can be used here? Now, each electron in any atom can be described completely by a set of four quantum numbers. So the first three quantum numbers describe the orbital, while the fourth quantum number describes the electron spin. Pauli's exclusion principle basically states that no two electrons can have the same four quantum numbers, which means that each electron will always have different quantum numbers. That's the reason why I said that when you have two electrons, no two electrons in the same atom will not have the same numbers, even if they are in the same orbital, even if they are in the same orbital and having the same orientation, the electrons themselves do not have the same spin quantum number. So an orbital in general, an atomic orbital, can hold a maximum of two electrons, and they must always have opposite spins, which means that one will be plus half, the other will be minus half. Next, let's discuss the factors that affect the atomic orbital energies. Now, the energies of atomic orbitals are generally affected by two main values. One is the nuclear charge, and second is the shielding by the other electrons. So the higher the nuclear charge, it increases the nuclear electron interactions and lowers the sub-energy level. So sublevel energy, when it lowers the sublevel energy, it is easier for the electron to get attracted towards the nucleus. Next is shielding. Shielding is where other electrons reduce the full nuclear charge to an effective nuclear charge. So think of it like blocking think of it like one blocking the other. So that reduces the amount of effect the nuclear charge has on the electron. This effective charge is the nuclear charge on an electron that it actually experiences, because there are other electrons that are taking more of the hit. The other one that can determine the factors that can affect the atomic orbital energy is the orbital shape also affects the sublevel energy. So let's start with the effect of nuclear charge. Let's say if you have single electron in the first orbit. So this electron here is the easiest to remove, because this sublevel is going to be the least stable sublevel. Now, when you start going towards, when the charge difference starts to increase, for example, if this is +2 and this is 1 minus, there is much more attraction from the positive charge, which increases the level of energy that is required to remove that electron. The same thing happens as you start increasing the charge, the effective charge on the nucleus. So the greater the nuclear charge, the lowers the sublevel energy. And it takes more energy to remove 1s electron from helium than from hydrogen. Next, let's talk about shielding and orbital energy. Electrons in the same energy level will shield each other to some extent. Now, electrons in the inner energy level shield the outer electrons basically. So think of it this like, think of it like a football game where one blocks the other from having the same effect. So think of it like, let's say if there is a quarterback that is running towards a certain person, and if there are two people in front of him, then the chances are that he might not have the same amount of force that he wanted to exert. So the farther from the nucleus an electron is, the lower the effective charge of that particular electron. So think of it this way. Let's say there are two electrons here. Now each electron here has an attraction force with the nucleus, but because they are negative and negative, they have a repulsion force with each other. So which means that when you want to remove this electron will basically push this electron out, resulting in the concept of shielding here, where it tries to push it out. Now when it is by itself, there is no chance for it to have the removal easily. So the more the number of electrons, the easier the electrons are to remove. So what is the concept of effective charge here? Notice that this here actually has an attraction force here. Now there is a repulsion force as well, which means that there is a net force that is acting on this, which is going to be less than the actual nuclear charge. The same thing happens for this atom as well, because notice that this atom has attraction with the nucleus, but it also has repulsion from these two electrons, which means here it is much less than the actual nuclear charge. So that net charge is what we call the effective charge. So this net charge is called as the effective charge. And this effective charge is what determines the higher the effective charge, the harder it is to remove the electron. The lower the effective charge, the easier it is to remove the electron. Now, next let's talk about penetration and the sublevel energies. So the one with the highest energy, the orbital shapes can cause the electrons in some orbitals to penetrate close to the nucleus. And this penetration increases nuclear attraction and decreases the shielding. Now the 2s sublevel is more stable than 2p because it penetrates closer to the nucleus. Now, what are the values of this effective charge? So these are some values of effective charge as you go towards higher and higher. The higher the orbital, the lesser the effective charge, and easier it is to remove the electron. Next, let's talk about splitting of levels into sublevels. So each energy level can be split into its sublevels of different energies. So this splitting is generally caused by penetration and its effect on shielding. So for any given n value, so there is a lower L value that determines how lower the energy sublevel is. So the least one in terms of the energy is S, the highest one in terms of energy is F. So it goes according to the order of S less than, P less than, D less than F. So this is the idea behind the splitting of energy levels. So the two things that are important in understanding where the electron will go is understanding where the electrons sublevels also matter. So the least energy one is 1s, the second least is 2s, next you have 2p, next you have 3s, 3p, and then you get 4s, because notice that 3d has a higher energy. That's the reason why 3d has a higher energy than 4s. That's the reason why you notice that even though the orbit is different, but the energy levels are the same here. Next, 4p comes next. Then you have 5s, because 5s has lesser energy than 4d. So this way you notice the sublevel energies here. Next, let's talk about electronic configuration and orbital diagram. So an electron configuration is indicated by a shorthand notation. The shorthand notation is NL-. N represents the principal quantum number. L represents the angular momentum quantum number. Ash here represents the number of electrons in the sublevel. So the angular momentum quantum number is not written as the number itself, but we convert that number into either SP, D and F. If angular momentum quantum number is 0, 1, 2 and 3, we write the corresponding electronic configurations. So orbital diagrams make use of a box, a circle or a line to represent each orbital in the energy level. So we use an arrow to represent an electron and its spin. So the one we write, so if one we write upwards, the other will be downwards. This can be written in either a square box or a circle or on the top of a line. So these are the three ways of writing. How would you fill the electrons here? First you fill the least energy level. Next, once you complete the least energy level, next you go to the second highest energy level, second least energy level. Next you go to the third least energy level. So this way you go from bottom to top. So you always fill the least energy first and then you go upwards. So what are the rules in terms of filling the electronic configuration, building the orbital diagrams? Is that first rule is the Aufbau principle, which applies to the electrons. Here electrons are always placed in the lowest energy sublevel available. So we always put them in the lowest energy sublevel. For example, hydrogen is in 1s orbital. The reason is because it's the lowest energy sublevel. Next, the next rule is the exclusion principle, Pauli's exclusion principle, which basically states that each orbital may contain a maximum of 2 electrons, which must have opposite spins. So if one electron is upwards, the other electron will be downwards. Next one is the Hund's rule. Hund's rule basically says that when orbitals of equal energy are available, for example, let's say p orbital, the lowest energy electron configuration has maximum number of unpaired electrons with parallel spins. So once you fill, we can only fill the electrons first, completely half fill the entire orbital. Only then we can start filling the orbitals once every one of them has equal amount of energy. The reason is because all of them here have the same energy, because all of them are p orbitals. So they have the same energy. That's the reason why we'll have to use this rule here. So let's take an example here. So they're asking you to write the set of quantum numbers for the third electron and a set for the 8th electron of the fluorine atom. So it's the third electron and the 8th electron. How would you write for this one here? First, notice the fluorine atom has an atomic number. The atomic number is 9. So which means that the first lowest energy sublevel is 1s. So we fill 2 electrons there. Next you have 2s. So this is 1s, 2. Next you have 2s here. Again, we fill both of them. You have 2s2. Next orbital is 2s2. So you have next is 2p. In 2p there are 3 equal energy orbitals. So first we fill all of them with 1 electron each. So we half fill the entire orbital. So now we are done with 1, 2, 3, 4, 5, 6, 7 electrons. Next we fill the orbitals which are left out. Now we completed the spin. So this here is the electronic configuration for fluorine atom. Here they are asking you for the set of quantum numbers for the third electron. The third electron is this electron. So for this electron here, we can say that n value is 2. We know that L value is S, so that you have S value for S, L value is 0. Next you have the one electron here, so the ml value is, notice that ml value depends on L, so mn value here becomes 0 as well. Next n value, sorry, ms value can be plus half. So if we consider the upward to be plus half, the downward one will become negative half. Next, they're also asking you for the setup for the 8th electron. So the 8th electron is 1, 2, 3, 4, 5. So notice here 1, 2, 3, 4, 5, 6, 7 and 8. So this is the 8th electron. Now pause the video right here and try to write down the set of quantum numbers for that particular atom. So you have to write M, L, ml and ms. So pause the video right here and try to write down those values. Now what would be the n value there? We notice that it's a 2, so second orbit. Next p, for p L value is 1. Now ml can contain minus L to L, so this is minus 1, 0 and 1. So the ml value becomes minus 1. ms here is, it's downward here, so we can write minus half. So these are the set of quantum numbers for the 8th electron of the fluorine atom. And this is how you number the electrons as well. So this is a diagram that depicts the orbital occupancy of the first 10 elements. So you notice that the first one is 1s1. Next you have 1s2. You have 1s2, 2s1, 1s2, 2s2. So once 2s2 is done, you have 2p1 orbital, 2p2, next 2p3, 2p4, 2p5 and then 2p6. So we always fill the electrons as per the energy level as we go upwards, and this is the way we generally fill the electron energy levels. Next, let's talk about partial orbital diagrams and condensed configuration. So in the entire configuration, let's take an example of a partial orbital diagram. So a partial orbital diagram basically shows only the highest energy sublevels that are being filled. Notice that this only shows the highest energy level, which means here if you take aluminum has a 13 number. So you start from 1s2, you have 2s2, next you have 2p6, next we have 3s2 and then we have 3p1. Here we are not going to show all of the configuration because notice that first orbital is filled and the second orbital is also filled. The only unfilled orbital here is the third orbit, so we are only going to write only those two separately. That here is the idea behind a partial orbital diagram, and this is how you write the partial orbital diagram. Now a condensed electronic configuration has an element symbol of the previous noble gas in square brackets. Now aluminum here has a condensed configuration, so we start from 1s2, 2s2, 2p6 is the configuration for neon. So we are going to basically write the noble gas configuration that is closest to the structure. So the closest structure to the aluminum here is neon. So then we write the condensed configuration as separately right after the noble gas. So this here is an example of the condensed electron configuration. So these reduce the amount of work that we need in understanding the orbital diagrams. That's the reason why we write both of them. So here this is a diagram that shows you the partial orbital diagram, the full electronic configuration and the condensed electronic configuration for the elements in from 11 to 18 with atomic numbers from 11 to 18. So notice that we are only writing the ones that are unfilled. So notice that we are basically writing the first part to be neon and then we are writing the rest which is unfilled. Next, let's talk about electronic configuration and the group. Now elements in the same group of the periodic table will have the same outer electron configuration, and elements in the same group of the periodic table exhibit similar chemical behavior. Now the outer electronic configurations will correlate with the similar chemical behavior. So notice that this is the important part. We have to have the same outer electron configuration. What does the term outer electronic configuration basically mean is that they should have one electron left in the s orbit. So notice that this group here has an electron only left in the s orbit, and you have the second electron, so they have the same s2 s2. Here they have the same s2p1, here they have the same s2p2. This is the idea of the first three periods that shows you the condensed electronic configurations and the similarity in terms of their chemical behavior. So because their electronic configuration is similar, their chemical behavior is also nearly similar. For example, all the 1A group elements, so 1A group elements are the elements in the first column. So the first column elements, all of them can be called as alkali metals. Alkali metals is when you put them in water, they'll displace hydrogen. So it's a common factor for all of these metals. When you go towards halogens, halogens when you mix them with a metal, they will form ionic halides, and it is applicable to all of these elements. So this is what we call as the chemical behavior correlating with the electronic configuration. So this is one of the reasons why chemistry became easier to understand. Next, let's talk about partial electronic configurations in period 4. In period 4, you start getting peculiar problems because notice chromium, notice copper. Notice that originally there is only two electrons. There should be filled one orbital and the other orbital should have the partially filled orbits. But notice that here, chromium here does not have the same, but rather has 6 unpaired electrons. The reason it has that is because of the fact that the electronic configuration here, so the first d orbital has to be filled before it can fill the 4s orbital. Notice that 4s orbital has lesser energy than 3d. That's the reason why the electron would rather fill the d orbital completely and then start filling the orbital in the entirety rather than directly filling the orbital there. So this is the idea behind. Notice that 3d is little lower in comparison to 4s, but in terms of energy 3d is higher. That's the reason why we see these discrepancies for chromium, for copper. So this is the idea here. So this type of filling is called as the partial filling, and this happens due to change in the energy levels. So we will discuss this as we go along in the lecture. So this is a diagram. This is the periodic table of all the partial ground state electron configurations of all the elements that are possible. And this is the hierarchy in terms of the periodic table. You go from 1s towards 2p and then you come back towards, so when between 4s you get 3d and you again go to 4p. So then once you go to 6s you get 4f, then you get 5d, then you get 6p. So this is the idea of how the, and this is the aid to memorize the sub-level filling order. And you start with 1s, then you go towards 2s, next 2p and then 3s, next 3p, next 4s, next 3d and then 4p, 5s, next you have 4d, 5d, 5p, 6s, this way. Now, so you have categories of electrons. So there are two types. One we call inner core electrons. These are the ones that are common with the previous noble gas configuration and any completed transition series. And you have outer electrons that are the ones in the highest energy level, so which have the highest n value. Then you also have the valence electrons. These are the ones that are involved in forming compounds. For main group elements, the valence electrons are the outer electrons. For transition elements, the valence electrons include the outer electrons and any d electrons. So any d orbital electrons are the ones that are involved in the structure. So we use the periodic table in the textbook and try to write down the electronic configuration for each of these elements. So they're only asking you to write condensed electronic configuration. So you don't need to write the full one. Even if you want to, you can try writing the full electronic configuration, but try to write the partial electronic configuration and draw the partial orbital diagram. So let's start with potassium. Potassium has a Z of 19. So the closest element for potassium, if you look at the periodic table, so potassium is K. So the closest element here is argon. So it comes right after argon. So we can write argon 4s1. So for this structure, we can write argon 4s1. And the highest energy one is the 4s1 orbital. So we can write the partial electronic configuration of 4s here. This is the condensed orbital diagram, partial orbital diagram. And this is the condensed electronic configuration. So use the same principle now and try to write down the electronic configurations for technetium and lead. So this is about electronic configurations. Next, let's talk about atomic size. So atomic size, so this is, there are three types of atomic radii. One is the metallic radius, covalent radius, and ionic radius. Metallic radius is the distance, the half distance between the adjacent molecule, the center of the nucleus of the adjacent molecules in a metal. Covalent distance is the half of the distance between the two nuclei of a covalently bonded atom. And this covalent radii, so knowing the known covalent radii and distances can be used to find the unknown radii. So let's start with the first one, the trends in the atomic size. So atomic size increases as the principal quantum number starts to increase. So as n increases, the probability that the outer electrons will be farther from the nucleus will also start to increase. In the same way, the atomic size decreases when the effective nuclear charge will increase, because there is more attraction and the outer electrons are pulled closer to the nucleus. So in terms of the main group elements, so the atomic size increases down a group and decreases across a period. So what is a group and a period? So in a periodic table, the vertical columns here are called groups and the horizontal rows are called periods. So this is the characteristic group and period that we talk about. So whenever we say go down a group, so down a group means from top to bottom, and across a period means from left to right. So for main group elements, atomic size will increases when you go down the group, and it decreases when you go from left to right across a period. So this is the common idea here. Notice that when you go towards the group, so you start noticing that the atomic size increases, but as you go down across the period, notice that the atomic size is actually decreasing. But it's not the same with respect to transition elements. Transition elements behave differently. There is a decrease in the across the period, and then again it starts increasing from the mid part of the group in transition elements. So this is the diagram that explains you the periodicity of atoms. Notice that the lesser the group number, the higher the atomic size. So group 1A elements are the ones that are the largest in terms of their original period. So now use only the periodic table and rank each of the set of atoms in order of the decreasing size. So this is the atomic table here. So they're asking you for first calcium, magnesium and strontium. So calcium, magnesium and strontium. So when you use the atomic periodic table, you notice that the calcium, magnesium is the first one. So magnesium is the smallest one. Then comes calcium, then comes strontium. So this is the order of the atomic size. Next you have potassium, gallium and calcium. So let's look at potassium, gallium and calcium. You have potassium, gallium and calcium. Now we notice that in the atomics under the period it actually decreases. The smallest one is going to be gallium, the second smallest is calcium, and then potassium. So you have gallium is the smallest one, then comes calcium, then comes potassium. So use the same principle now and pause the video right here and try to solve C and D and try to write the order of decreasing atomic size. Next is the trends in the ionization energy. What is ionization energy? So ionization energy is the amount of energy required for the complete removal of 1 mole of electrons from 1 mole of gaseous atoms or ions. So the atoms with low ionization energy generally tend to form cations. So cations are generally positively charged atoms. Atoms with high ionization energy will form anions. So the anions are the atoms that can form negatively charged atoms. Now ionization energy generally decreases down a group and increases across a period. So it decreases from top to bottom. The reason mainly is because the atomic size increases. So therefore it is easier to remove the outermost electron because the effective nuclear charge is much lesser and the effective attraction between this is much less. and it increases across a period. So from left to right it increases. The reason mainly is because the atomic size becomes smaller. As the atomic size is smaller, there is more effective nuclear charge. The more the nuclear charge, the harder it is to remove the electron. So when you see, as you go down the group here, it starts decreasing, but as you start noticing that across a period, here it actually increases. So use the same principles as before. Now try to write down the atomic in terms of the decreasing ionization energy. If you look at helium, chrome, krypton and argon, so helium here is the one that has the highest. Next you have krypton and argon, so krypton and argon. So helium is the highest, then argon, then krypton. So helium greater than argon, greater than krypton. Use the same principle now and try to solve B, C and D. Pause the video right here and try to solve B, C and D. Now, ionization energy is not one energy, it increases as you start removing more and more electrons. For example, when beryllium atom, when you remove the first electron, the energy is less. And once you remove the second electron, it increases. But when you start removing, looking for the third electron to be removed, the ionization energy increases rapidly. So this is the diagram that explains to you how much ionization energy is required to remove electrons. As you start noticing that it increases to a ridiculous value when you start going towards the core electrons. So core electrons are the innermost electrons. So because there is much more effective nuclear charge, so it starts increasing rapidly. So because the effective nuclear charge increases rapidly, there is a sharp increase in the ionization energy required to remove the electrons, and it goes towards the level of megajoules per mole, which is too high to easily remove the electrons. So they're asking you to name the period 3 element with the following ionization energies and write its electronic configuration. So notice that here you start noticing a small change in the ionization energy, and then from here to here you notice a rapid jump, which means you have to remove the first 5 electrons. So these are the atoms that have 5 electrons in the outer shell. So the only element that has the 5 electrons in the outer shell is phosphorus. So because it has 3s2 3p3, so this is the element that you can find.